Today we are on the Unit 3, the basic data structure, Lecture 2, Q. In the previous lecture, we talked about stack, and that's a while ago. But right now, we resume this discussion for data structure. Now we are on Q. So let me bring up the whiteboard. So basically, in the past few weeks, we actually working on the two types of the C link structure. We basically finish the C link list, right? And originally we teach the C array as well. And we also have the homework for C double plus version for both of them. And then we also cover the C tree node, right? And we already covered this red one's course, the Python step so far. So today we are going to talk about Python Q and Python DQ. And the next talk we are going to talk about Python priority queue. And that will be the maybe Wednesday. We'll talk about that. And then after that, it will be Python tree and Python graph. That will be primarily the basic part for data structure will be completed. So here, this linked list for C double plus will be made to be generic. So you will be able to support all the design for Q, DQ, priority queue using the linked list. And also, it can also be implemented by C array for everything like here. And tree structure, if you have heap tree, you can actually support the prioritized tree, queue actually. And of course, the C tree node can support tree. So we are actually start to look at the combination of different possibility in the data structure and data structure implementation. So now let's look at Q. And we look at stack. Stack is the last in, first out data structure. So now we actually focus on Q. And Q actually is first in, first out. It's different from the stack. So let's look at the diagram. So what is a queue? A queue is an ordered collection of items where the addition of new items happens at one end. It's called rear. And the removal of the existing item occurs on the other end. It's called front. So you basically has a buffer. Sometimes queue is also called as buffer. Okay. And the purpose of a queue usually is also buffer. So basically, you have something like this, a waiting room or something. And here is a consumer, here is a producer. You put something in, you call it the producer. And you take something out, it's called consumer. Okay. And you keep pumping data into this queue, and then the other side take it away. Okay. But as long as it's not empty, you can continue to consume it. As long as it's not full, you can continue to stop data into it. This is called FIFO or buffer, and sometimes called a bounded buffer. And it's actually a queue. Queue is like that. It's a first come, first serve. So first get in, you can get out. So one way to look at this is like you go to the doctor's clinic, and then there's only one service room or diagnosis room, but there is a waiting room, and other people have chairs sitting here waiting for the call, for your number to be called. And then each one will one by one, first come, first serve, to go into service and get out. And the people come in, if there is an empty seat, he will be able to see it. So the doctor's waiting room is also a queue. So queue provides a few functions. Number one is buffering. Number two is provide actually the uninterrupted service. And what is uninterrupted service? From the doctor point of view, He can sit here for 12 hours. If the queue is in almost like field condition or half field condition, he can sit there and actually he will keep looking at some patient all the time without breaking down. So that's the purpose for the anti-interrupt service. And buffering, you actually is able to buffer the whole people so people don't will not go away. Okay, but there is an issue. There is a problem. That is a latency problem. You actually need to think about when people come to your waiting room, how much time can he tolerate, really tolerate? So queue have these different design considerations. That is basically how long the queue can be and how much element should you be buffering. Okay, so Eric, is that okay?
Yeah.
So that is a queue. So it's basically you can pump data in and take data out. Okay, as long as the queue is not empty, you can pump data out, get data out. And if your queue is not full, you can keep pumping data into the queue. And sometimes the queue can be programmable of different lengths, and that will not have the full issue. So sometimes the queue is full, sometimes no. And if you use the linked list, there is no full condition for the linked list type of queue. But if you use an array or some vector with some capacity, then you might have the is a full situation. If empty, you always need to check whether the queue is empty or not. So computer science also a common example of queue. Our computer laboratory has 30 computers networked with a single printer. So that is, if there is only one server, say only one printer server, and then there are 30 students' computer connected to it. So there is a queue. Everybody's job being submitted to there, and then you will wait for a certain time until it got serviced by the printer. So that is called queue. So usually if you look at printer, there is always a printer queue. Actually the printer keeps serving some job from certain application, and then if it finish, you will pick up a waiting task that is in the queue. So one of the example is the printer queue is a example for queue. Second is a event queue. Event queue is like I have this window environment and I click somewhere, that mouse click will be buffered in the event queue. And then I may also have keyboard activity that will be put into the event queue. So it actually has the first come, first serve situation as well. Or you go to a line for ticket ordering or registration if you are on the website. So the order comes from the whole wide world, and then you actually have that ticket ordering job come into a certain website that will actually serve to process the ticket ordering, and then those jobs are in a queue and they will be done in a one-by-one first in, first out situation. And these are non-prioritized queue. And there may be some prioritized queue. What is a prioritized queue? Say you go to Southwest airline, you are trying to board in. So there's a person and there's a gate. There's a person sitting down there, right? So you have your A pool or B pool or C pool, and there's some pool actually for VIP, and also those people travel with kids, little kids. Okay, so you basically, when you get into the queue, you are based on the number you are assigned, and then one by one you go into the service. So it's no longer first come first serve. It's first come based on the priority level you have, you got served. That's called prioritized process queue. Is that okay? Hello?
Yeah.
Is that okay? It's not fully first in, first serve. It's actually prioritized for service serve, such as the Southwest system. Okay? So here I do not touch the technical part for the queue. just that you know about what is a queue and what is a queue for. So basically right here, we have a printer, and then there are 3 computers, each one submit a job. So those jobs being transmitted to a server that queue them up. And then one by one, those jobs are served by the printer. And then this one is an event queue. Your Java script service engine gets some call that actually from your website clicking or something. And those will be put into the web API, the AJ or queue or event queue. And those queue being put into a callback queue. Each one callback is a service function or the event handler function. And whenever they are called, they will be put into the event loop to process. So there is only one server called event loop. And each one of them, those mouse click, screen resize, or your keyboard click is a event that need to be processed by the queue. We call it event queue. And then event queue actually got serviced by the event loop. And event will find a handler for that specific event and process it. So this is called the event queue. And here it actually is the third kind of queue. It's called prioritized queue. So when I have a CPU, right, and then I have several jobs, and those jobs actually are basically put into some waiting queue. But this waiting queue actually is prioritized. Some process a higher priority, some process a lower priority. So you actually look at the higher priority one first. And then if you finish, you look at the second order process, and then look at the last one. Okay, sometimes after a certain service, you will adjust. Some of the jobs stay in the queue for too long. You can pull it up to the higher priority queue, and that it got serviced. So prevent the process to go into the starving situation. Okay, some process, if it's in CPU, never been called by or serviced by the CPU, then that process can never be run. But some of the important jobs that need a real-time response will be programmed to receive higher priority, and they will be processed first. So this one is using the prioritized queue. So queue actually is not one single data structure. It can be of different kind of data structure and depends on the application. But here we actually look into more generic queue. So queue is an abstract data type. You have a queue that is the constructor. So you create a new queue that is empty. It needs no parameter and return an empty queue. And a queue can easily be implemented by a linked list. So that's easy. Then the next one is the in queue. So the in queue actually, because it's a queue, so in queue usually you will put into the head location. You put the data into here. But when you dequeue, you remove the data from the tail of your linked list. So you push in on this side and pop in on this side. That's your queue. And check it if empty. If the linked list is empty, it will be empty. Size, you just return the size of the linked list. Is that okay? Is that okay, Eric?
Yeah.
So basically, all the function we see here can be easily implemented by linked list. So basically, you build your data structure based on node, and node is actually called by your linked list class in CC++. And then you build another level called queue. That's a class. And queue call this one call this one. This one can be structured. This one can be structured, or it can be a class. But this one I would definitely suggest to be class, because all of these are better be described in member function. And the node, because it's process, you use pointer, stay in structure is okay. Is that okay? So in terms of judging of whether you use structure or use a class, if you actually usually have the member function type of operation, you would prefer it to be class. But if it is quite simple, you just need a few calculation, and you don't want to get involved with OOP, then the structure is easier. You don't need to declare public or private. That actually is easier to do. Is that okay, Eric? Is that okay, Eric?
Yes.
So the next one, we actually starting with a queue that's empty, then we enqueue, so there's a 4. Then we enqueue is doc. Python can allow the linked list to be of different type. So, but how can we handle the data of different type in what? In C++ or Java? So Eric, how can we handle
generic programming?
Yeah, so you create a class, so called something called string. Your own string X, right? And this is number X, right? And number X and string X all inherit data X. So you just put everything as data X, and then pointer D1 equals new, like string X. Is that okay? And then the D2, you new as number X. And then each one of them being put into the queue, and the queue needs to be declared as when you do queue. When you do queue, you need to create it as the data X type of queue with generic property. So next, I will need you to convert your linked list to become a generic linked list. Is that okay? That actually will help to solve this problem. But in Python, actually, this generic problem already been solved. It allows different type of the data be enqueue. So we can also enqueue a true in there, and then we can check the size, that's 3, and then we check it's empty or not, it will be false, and then we enqueue 8.4 in there. So 8.4 put into the real part, and then we dequeue, we get the 4 out, we dequeue, we get the doc out, and we check the size, it will be 2, okay? So these are a simple process for a operation on queues. So the next one is implementing a queue in Python. So implementing the queue in Python is very easy. When you need a queue, you just create a self that the queues are items to be empty. So if you create a class in C++, if you have a class in C++, okay, you pretty much just need to, in your public or your private, you probably need to have something called linked list. It's called item or something like that, right? And then check empty, you can do the list that is empty or something. Just return that value is good enough. Enqueue is to do insertion on the head location. Dequeue is just do pop out or remove at the end. Size is just return the length. Is that okay? Eric, is that okay? Hello?
Yes. Yes.
So it's actually not really hard to move from your linked list. So the generic linked list is very important. Then you can use that for for stack, and also for this one called queue, and also the coming one dequeue, and the ordered or prioritized queue. So this one we have an online demo. So let me actually break here and go to the online course. So let's go to the online course. So here we are on queue. Right now we actually are on this queue, implementing queue in Python. Okay, so this is here, and here it says a program called queue class. And this queue class actually, if you look at it, it actually do create a queue, enqueue4, enqueue doc, enqueue true, and then check the size. Okay, so that's the program we have right here. Let me actually minimize a little bit. Okay, and after that, we actually can go for one step. So initially you go into Q equals Q, so you create a Q object that has the init function, DQ function, InQ function, its empty function, and size. So these are all the member methods. And your friend, your Q will be a pointer to that object. So basically you have a Q that has a pointer to that. And the next one, you basically call the InQ. So you go into InQ, and then basically you will create your items to be empty. So you actually add an item that's a data field for this Q. So that now the data field, now this the QQ will have these different member method and a item member data or instance data. So after that, you basically go to InQ4. So you actually will put the data into this one, the queue. And after that, you will InQ dog. You will be inserted to the 0 location. And after that, you will InQ dog, and dog will be inserted to the 0 location as well. Okay, so you have the dog in there. And then the next one, you actually will insert true. Same thing, you will be inserted at 0 location. Okay, so that's the end of the queue instance, and then you print out the size. So that actually give you 3. Okay. So now here, let's work on this self-check problem. So we have suppose we have this queue, right? Q is equal is InQ hello, InQ dog, InQ3. Then you DQ. Then what is the item left in the queue? Eric, can you work on this one? Can you work on this one? Hello? Can you work on this one? What would be the result? You InQ hello into dog InQ3. And then you DQ.
B. B
is dog and 3. Yeah, B is kind of the best, but that's, yeah, about the best, but actually older, I would have question is older. So basically you would have something called hello, right? So hello will be put in first, right? And then you InQ dog, so dog will be next, so hello will be here, and then dog will be here, right? So the next one, you InQ3, and then you will delete this one, right? But remember this location, 0, this is 1, so I would prefer to be written down as 3 dog, because you always remove data at the end, right? So I believe among the 4 answer, I will pick B, but I would say the hello 3 dog will be better than this one's dog 3. Okay, the next one is a simulation hot potato. So what is a hot potato? So there is actually a ancient problem called famous Josephus problem. Okay, let's look at Josephus problem video. So here, let me adjust my sound. This one is very important. Okay, the Josephus problem is actually quite famous problem in data structure and algorithm. Okay, so have to pay attention to it. Okay, let me make the sound louder. Okay. So here, let's do. Let me see. It should be this one. This one is Josephus problem.
So it's called the Josephus problem. It's based on something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and they didn't want to get captured. So they decided to come up with.
Okay, so Jewish soldiers surrounded by Roman fighters. Okay, And did you hear the sound? Hello? Did you hear the sound?
Yeah.
Okay, I'll continue, okay? So Joseph, the Jewish people surrounded by Roman people, and Roman will kill them anyway. But they have the agreement that, okay, that's one kill each other, so nobody will be killed by Roman. Everybody, the last one need to suicide. But a guy, he actually decided that this guy called Joseph, actually, he want to be the last one, and he doesn't want to suicide. Okay, so he's actually the betrayer, but he want to calculate where should I stay so that I don't need to suicide, be killed by other people. So the rule is that if I study from this orange person, he will kill the one next to him. Okay, that's C.
With a system to avoid getting captured or suicide. So they'd sit in a circle, and the first man would kill the guy to the left of him. The next remaining living person would kill the next remaining living person with their sword, and they go around like this until there's only one person left, and then the last person would have to commit suicide, of course, rather than get captured. And the story, at least the story I was told, I'm not sure this is historically accurate, was that Josephus preferred capture to suicide, but he worried that if he said this, the other soldiers would turn on him. And so he wanted to figure out where should he sit within this circle in order to be the last man living, and then he would surrender rather than. That was the problem. It's a little tricky, so let's do a smaller example. Let's say there were 7 people. And so just to be clear, the way it works is person number 1 kills number 2. Person number 3 kills 4. 5 kills 6. But now things get a little harder to kind of see in advance, because 7, there is no 8, so 7 kills 1. 3 kills 5. 7 kills 3. So 7's the winner. 7's the last one left over. For Josephus, there were 41 people. He needed to figure out where to sit. The mathematical problem is if there were n people, where's the winning seat? When I learned this problem, I was in high school. And it was one of the first problems that got me to understand how you approach difficult and math problems where you don't know the answer in advance, where someone hasn't shown it to you in advance. And it was a professor of mine. His name was Phil Hanlon, who played a big role in kind of leading me to math. And he suggested what we should do is we should gather data. Just take various values of n and just do it by hand and start looking for a pattern. I don't know, maybe we should just do that. N is the number of seats, and W of n will be the winning seat. And so what we know so far is that n is 7, W of n, it turns out, is also 7. And so what I would do is I'd start doing some other values. So I don't know, why don't I do 5? So 1 kills 2, 3 kills 4, 5 kills 1, 3 kills 5, the winner is 3. I guess there was no reason for me to skip 6, so why don't we fill in 6? 2, 3 kills 4, 5 kills 6, 3, 5 kills 1, the winner is 5. So if you're watching, you might already start to notice some patterns. For instance, they're always odd. I mean, that's maybe the first thing you notice. And you can start to ask them, well, why are they always odd? And maybe you can already see that, right? The first loop around, all the even people get killed. So you can even with just a tiny amount of experiments start to see some patterns.
So you don't want to sit in the even seat.
Don't sit in the even seat. No. And maybe we're even getting some glimmers of other patterns. But before I really try to phrase those, I'd like to fill in the table a little bit more. So let's do some. So if there's only one person, well, that person's the winner. So that one is easy. There's 2 people. 1 kills 2. 1's the winner. If there's 3 people, 1 kills 2, 3 kills 1, 3's the winner. If there's 4 people, 1 kills 2, 3 kills 4, 1 kills 3. If there's 8 people, 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8. 1 kills 3, 5 kills 7, 1 kills 5, winner is 1. So it was 1, 1, 3, 1, 3, 5, 7, 1, 3, 5, 7, 9. And you could keep going, but maybe you can see the pattern now.
I think it's 13 or 1.
No, good guess, actually, but it's not a 1. So
Really?
let's do 13.
This is good. I don't know then. I can't see the pattern.
So as you see, it's jumping by 2 each time, but then it resets at some point. And I want to go back to this. So we'll see what 13 is quickly. So we didn't reset that. I claim we won't reset it the next one either. 14 will be 13. And here, by the way, we're starting to make predictions. It's worth noting even though we maybe can't say exactly what like 178 would be, we're starting to see the pattern well, and so we could make a prediction. So you could guess, is it really true that 14 is going to give you 13? And we could do it out, and you'll see, in fact, that's what you'll get. So we're getting some understanding. But I want to go back to this point you had. You asked if it was going to reset and go back to 1 then. And the answer was no, and it's worth looking, because this is the next thing I was going to do. Where do we get the 1? So if you look for a sec, there's something very special about the numbers that give you 1s. It's the powers of 2. And so maybe you can now guess that if I put in a 16, I would get a 1 back. And that'll be right. And that's actually going to be a real key in unlocking this. The professor I was learning this from made a really big point out of this. And
okay, at this point, can you draw some conclusion on this problem yet? Hello?
Pattern.
What?
Pattern.
What kind of pattern it has? It said that actually every time when you actually go to 2 to the power n, it will actually return to 1. So that's what it said, right? You hear that? So basically 1 you will end up with 1, right? 2 you will end up with 1, and then 8 you will end up with 1, 16 you will end up with 1, and then 32 you will end up with 1. Other than that, actually from here to here it will be 1, 3, 5, 7. From 8 to 15 will be 1, 3, 5, 7, 9, 11, 13, 15, right? So here actually something like that, right? And then from 16 to 32, it will be 1, 3, 5, 7, 9, 11, 13, 15, until 31. 31 will be 31, and then 32 will return to 1. So what did this tell you? What does this tell you? What does this tell you actually? So whenever you have some 2 to the power n, you will return to 1. If it is not 2 to the power n, what will happen?
It doesn't go to 1.
What?
It doesn't go to 1.
Other than that, what information you figure out?
It repeats itself.
Repeat what itself. So which one will be the itself? 2 to the power n minus 1 will be actually itself. Right? 2 to the power n, like 7 will be 7, 15 will be 15, 31 will be 31. Right? And then 2 to the power n will be go to 1. Right? Is that true? Right? Oh, here I'm missing 4. So here actually 2 will be 1, and then 3 will be 3, and then 4, 5, 6, 7 will be something like that. So let's look at the number again. Let's look at the number again. Okay. Let's look at the number again. Look at this pattern. So this problem actually more like a discrete math problem. So you have a 1, it will be 1. 2, it will be 1. 3, it will be 3, right? 4 will be 1. 5 will be 3. 6 will be 5. 7 will be 7. So how many here, how many here, how many here? And then how many next? 8 will be 1. 9 will be 3. 10 will be 5. 11 will be 7. 12 will be 9. 13 will be 11. 14 will be 13. 15 will be 15. So how many numbers from here to here? Here actually it has 1 number. Here it has 2 number. Here it has 4 number. Here it has 8 number. So this one is 2 to the power 3. And then after that, a number will be repeating from 1 to the number. Here it will be 2 to the power 2. Then the following 2 to the power 2 number would is starting from the circle, the 1, 3, 5, 7. So here it will be 2 to the power 1. Then you will have 2 to the power 1 number will be the R number from 1 to the number. Okay. So then how can we find the number that corresponding to certain certain number n? What would be this number be? What would be the number? N plus 1 square would be n squared plus 2n plus 1. That's the R number. Okay, the key is from that equation. So let's look at its further explanation. Okay.
And I thought, you know, well, I don't know what the general answer is yet. And he made a big point. If you know something, prove it and make sure you really understand that one thing. And that often unlocks the rest. So he really pushed us when I was first doing this to try to state a conjecture and then prove a theorem based on what we just saw here. And so that's what I want to do. So here's the conjecture, is that if n is a pure power of 2, then the winning seat is 1. I want to think about this for a second and maybe see why this might be true. So let's do the next biggest power of 2, maybe the biggest one I can bother writing. So let's do 16. So I want to do one pass through the circle. Take out all the evens. And now 15 has just killed 16. I'm going to put a little dot here so we remember it's number 1's turn again. And it's number 1's turn again, and we've removed all the evens, and what's left is therefore exactly half as many. So if I relabeled it this way,
okay, so it become a problem. You
kill
kill the first one, you become a problem of what? You kill the first one, you become a problem of, from 16 jump to problem of 8. Right? And then you kill another round, you jump to a problem of 4. Then you kill another round, you jump to a problem of 2. Then you kill a round, you become problem of 1. So basically, that's why 2 to the power n always end up with 1. So that's proven. Is that okay? Because the first round, you have 16 people. You kill those guys already being killed, you become a problem of 8. So actually, the problem of 16, you started from 1, you will end up with 1, 2, 3, 4, 5, 6, 7, 8. The 8th one is 15. So the next round you continue to kill, this one still be 1. Or you always 1, so that it will be the last one to be killed.
The circle once I get rid of it, I have half as many, and I'm back at number 1's turn. So now if I do this again, the same thing ought to happen, right? I should kill all the evens under the new labeling, and now there are
still the one still be 1,
and it's still number 1's turn.
Yeah, and you keep killing.
So those guys, there's 2 people.
Yeah, 2 people.
Still number 1's turn, and now 1 kills that. And it's still number 1's turn. And
yes.
So let's say we believe that. We know what happens.
So 2 to the power n that equals already been solved.
Between the pure powers of 2.
Yeah, and then now is the problem in between.
We know what happens at 8, and we know what happens at 4. But between them, it goes up by 2s until at this point, if I added 2 to 7, I'd have a 9. It would be too big anyway. So that's our reset. But we knew it was going to reset since it's a pure power of 2. So how do we explain this jumping by 2 phenomena in between? And so what I'm going to do, I'm going to just mention that for any number, you can write it as a big power of 2 plus something else. Take the biggest power of 2 you can subtract from a number, and then what's left should be smaller. When you express a number in binary notation, you choose zeros or ones, and that gives it as a sum of a bunch of powers of 2, and you just choose the biggest one. So 77, the biggest power of 2 I can get is 64. And then what is it? It's 64 plus 13. So then for 13, the biggest power of 2 is 8 plus 4 plus 1. Did I do this right? 72, 77. There you go. And these are all powers of 2. And this is unique. This is the unique way to write 77 as a sum of powers of 2 where no power is repeated. That's a key point. So if you wanted to take a general number, take the biggest power of 2, 64, and then the remaining part, 12, 13. I'm going to call this part 2 to the A, and the remaining part I'm going to call L. And I claim that this L is going to tell us which of those odd numbers between is going to show up. So let's see how. How about we do 13? N is 13. This is the binary expansion, but using our new method, the 8 will be the 2 to the A, and the 5, which is the 4 plus 1. That'll be the F. And here's the thing that's going to happen with the F. I'm going to do 5 steps. So 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8, 9 kills 10. So now I've dropped L people, and it's number 11's turn. Now watch what happens. How many people are left? Well, what's left is a power of 2. And we know who wins in a power of 2. It's whoever starts. The first killer. So now, if we go from here, I claim that 11's going to win. And just watch. It's going to be 11 kills 12, 1, 3 kills 5, 7 kills 9. Back to 11, and now there's only 4 people left. 11 kills 13, 3 kills 7, back to 11, 2 people, 11 win. And so this is really the key to the final answer, which is if you've written your number as 2 to the 8 plus L, after L's steps, whoever turn it is going to win, because it's going to be their turn. There'll be a power of 2 left. And so the winning seat will be 2L plus 1, if you write it in this way. So that's whose turn it will be after L steps. The theorem, or claim, is that if you've written n in this way, so if n is 2 to the 8 plus L, where L is less than 2 to the 8, it has to be strictly small. So in other words, 2 to the 8 is the biggest power that sat inside of n. Then the winning seat is going to be 2L plus 1. So we've already seen it was true here, right? L was 5, and the winning seat was 11, which is 2 times 5 plus 1. And if you start going back through, you'll see the same thing for all the answers. We've already really illustrated the mechanism, which is after L steps, it's the turn of person 2L plus 1. And after L steps, there are a power of 2 number of people left. And when there's a power of 2 people, the first person is the first person who kills. That's who's going to be the winner.
Let's see if Grady has learned.
Yeah, all right, let's do it.
I think I followed. Now, in the Josephus problem.
Yep.
So is that clear so far? We see just first 2L plus 1 part.
Mm-hmm.
Okay.
With Josephus and 40 soldiers.
That's right. Oh yeah, we got to go back and do that.
All right, so we've got 41 people.
So n is 41.
So 41 actually is up to 32. So it's like 32 plus 8,
It's going
right? And the L right now is 8. So it's a 2L plus 1. It should be
So 2
17.
lots of 9.
Or 9, I'm sorry. L is 9. So it will be 17. I mean,
So we want to
19,
sit
I'm
in
sorry.
position 9, 10.
There you go. You want to sit in the 19th chair. So here we go. We're going to do n equals 41.
Okay, waiting their fate.
It's not a very good circle, but I know. Should I redo this?
No, you're okay.
Okay, there we are. So it got a little tight at the end.
Look
All
at
right.
that. This is a lesson about planning ahead.
Yeah. Okay. So let's do it. 1 kills 2.
We're losing our even numbers.
Yep. Okay. 41 kills 1. And 19 kills 35, and there we go.
All right, I was right.
There we go, 19. I'll note one other thing in this problem, which is kind of fun. So this formula I wrote can be interpreted in binary notation. When we wrote a number as a sum of powers of 2, this can be re-expressed in binary notation. What was this? 32 plus 8 plus 1. So that's 2 to the 5th plus 2 cubed plus 2 to the 0. And binary notation, the digits correspond to the various powers of 2, and all the digits are 0 or 1. So 41 in binary notation would be 1 copy of 2 to the 5th, 0 of 2 to the 4th, 1 of 2 to the 3rd, 0, 2 squared, 0, 2 to the 1st. Here's a trick for the Josephus problem, which I won't justify, but it's super cool. You can try it on your own. The way to find the winning solution, if this is n, the winning solution in binary is you take the leading digit and you put it at the end.
yeah.
So in other words, I claim that if I write 0, 1, I take this part and then I add the first digit to the end, that number in binary
19.
code is, well, let's see, it's 2 to the 0 plus 2 to the 1 plus, I skipped 2 squared and I skipped 2 cubed, and I add 2 to the 4th. So it's 2 to the 4th, 2 to the 1.
Why?
2 to the 0, which is 16 plus 2 plus 1.
Why? Why is that? Why you move the top 32 will be the plus 1 will be it? Hello?
I don't know.
Say the example it has given, this one actually is what? Is the 2 to the power n plus L, right? And this one actually is like for 41, is a 41 that it used, right? It's actually 101,001, right? So this part actually is L, right? So this one actually times 2 means you shift left by 1 digit. So that one is 2L. And it is 1 add to here, this is plus 1. So the number he's trying to explain, this one actually is 2L plus 1. It is actually the remainder of the digit put in the 1 at the end. That's actually the 2L plus 1. Okay, that's the 2L plus 1. Is that okay?
Mm-hmm.
Is that okay? That's the
Yeah.
2L plus 1 part. Okay. And the mathematical behavior behind it is actually you keep killing each body, right? 1, 2, 3, 4, 5, 6, 7, 6, 7, right? 8, 9, 10, 11. Say in this case, you divide it by 2 every time. You divide it by 2 every time, so you get some number. Say the first one actually your problem coming from what? Originally coming from actually you have 11, right? And 11 will become what? The next number is divided by 2. You got 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You get 6. So actually it's like 2 times 5 plus 1 because you kill 5 people, right? And there's a remainder 1, right? And then the next time you actually divide it by 2 again, right? So starting from your 11, that's the number 1. So you divide it by 2 and then plus 1. So that becomes actually 5 plus 1. So you actually kill this one, and then 3 kill 5, 7 kill 9. The next one actually, the first one actually you from 11 actually you become 6, right? Because of 5 plus 1, so it's actually 6 people. Okay, and then 6 people you actually divide by 2, you become 3 people. So the next one it becomes 3 people, and the next one 3 divided by 2 it actually is 2 plus 1, so actually become 2 people at the last block, and then after that so it basically is checking your remainder, and then you will point out where this location it will be. Each time is divide by 2 process. If you look at this problem, each time is a divide by 2 problem. So the next one actually 11 kill this guy. Let me see. Oh, this one 3 kills 7, and then it's the one 11 kills 3, and you will have that survive. Okay, so that's what it's trying to claim. It's a 2L plus 1 for the remaining part,
which is 19, which is exactly what the winning sequence. And so there's this super efficient way in binary code to jump straight from the number n to the winning number w. So if you're writing your numbers in binary code, the pattern would have been even more quickly apparent. Isn't that cool? Yeah.
So basically, the answer is like you actually have the number n, you convert it into binary, and then shift the most significant bit to the n. That's it. That's the 2L plus 1. Is that okay? The final conclusion is that you get the n, right? And you will get n's binary condition, and then move that first digit to the n. That will give you 2L plus 1. So the theory is actually behind it. The math actually is to find the number. The exact number will be, if your number is actually 2 to the power n plus L, the answer should be 2L plus 1. No matter what L this one is, the answer will be this one. And because this is this one, so if your n actually I'm sorry, this is a. If your n equals this and that one actually was this, you actually would end up with this one because it's the first digit, so it's 2 to the power whatever, and that is a L combination. And then you move that bit to the end, that will give you the 2L plus 1. So the key point is that how can you figure out the 2L plus 1, the remainder part plus 1 will be your solution. That's the key. How to understand that when you have a 2 to the power L, a power A plus L, and that L, 2L plus 1 will be your remainder, the winner number. That is the key. In the process, in the middle, when he explained that,
bunch of powers of 2.
That 2L plus 1 power.
So if I relate,
so that 2L plus 1
power of 2 I can get is 64, and then what is it? 64 plus 13. So then for 13, the biggest power of 2 is 8 plus 4 plus 1. Did I do this right? 72, 77. There you go. And these are all powers of 2. And this is unique. This is the unique way to write 77 as a sum of powers of 2, where no power is repeated. That's a key point. So if you wanted to take a general number, take the biggest power of 2, 64, and then the remaining part, 12, 13. I'm going to call this part 2 to the A, and the remaining part I'm going to call L. And I claim that this L is going to tell us which of those odd numbers between is going to show up. So let's see how. How about we do 13? N is 13. This is the binary expansion, but using our new method, the 8 will be the 2 to the A, and the 5, which is the 4 plus 1, that'll be the F. And here's the thing that's going to happen with the F. I'm going to do 5 steps. So 1 kills 2.
Okay, to be short. Let me explain how this L can be. You have from 4, 5, 6, 7. This one will end up with 1, 2, 3, 1, 3, 5, 7, right? Because that's your observation. 1, 3, 5, 7, right? So here you actually, this one is like 4 plus 0, 4 plus 1, 4 plus 2, 4 plus 3, right? This 3 number is that. And you corresponding to here 1, 3, 5, 7. So this actually is the ordering of the remainder. The remainder is actually called L. And actually this number is 2L plus 1. That's the observation we got from there. Is that right?
Yeah.
Yeah. So basically it's the observation is from here. You already know that it's 1, 3, 5, 7. We already know that 1 is 1, 2 is 1. 3 is 1. 3 is actually 3, I'm sorry. 4 is 1. 5 is 3. 6 is actually 5. 7 is 7. So it tries to catch up every time by 1, by 2, by 2, by 2. Okay? So actually when you look at this, a certain 2 to the power n section plus the remainder, L is actually the remainder. So the remainder times by 2, you will get whatever you want to have. You know. So the maximum remainder would be what? The maximum remainder you get is what? In between your 4 to 7, the maximum remainder by divided by 2 to the power n would be what? Because your number is 2 to the power 2n will be 2 to the power n plus some remainder. So this L will be always smaller than 2 to the power n. The maximum is 2 to the power n minus 1. If you are working on 2 to the power 2n, you know, like A is 2n, n is 3. So if you actually, any number between 2 to the power n and 2 to the power 2n, 2n is 8. And between 2 to the power n and 2n. So n is 2 to the power 2, n is 2. And 2 to the power 2n, I'm sorry, 2 to the power n plus 1 is actually 8. Not 2n, it's n plus 1. So in between that, your remainder number maximum would be 2 to the power n minus 1. So for 4, the maximum remainder would be actually 3. It will be less than your 2 to the power n a number. It's always like that. So actually within that you actually 2L plus 1, because the number will be 2 to the power n minus 1 times 2 plus 1, it will be less than 2 to the power n for sure. N plus 1 for sure will be less than that. So there's no problem. You will catch up the number, but it won't pass it. Okay? Is that okay for this one? So that's actually, okay, then that actually related to this Q problem. So the Q problem right here actually is, the Q problem we will see right here is that it's actually a queue, and each time we retire one guy from the queue. Is that okay? This hot potato problem is like each time we retire one guy from the queue. So it's a queue problem, but it's actually every time you retire one guy. So hot potato, we have Brad, Bill, David, Susan, Jen, and Ken. Okay. One of the typical applications for showing the queue in action is to simulate a real situation that requires data to be managed in FIFO format. To begin, let's consider the child's game, hot potato. In this game, child line up in a circle and pass items from the neighbor to neighbor as fast as they can. At a certain point in the game, if the action starts and the child who has the item, say the potato, will remove from the circle. So play continuously until one child left. So this is similar problem. So the game is modern day equivalent of famous Josephus problem. So based on whatever this one is, okay, some count every man and some allow the last man to escape from horse, whatever. So here, this one is the Joseph problem that we know already. So Joseph number is like Joseph of n will be something you continue to divide by 2 until you actually Joseph of n is something like this. Okay, because you want to have the remainder and then there's a plus 1. You keep doing that every time you take 2 pair out, and then until there's only one survive. Okay, so that actually is the problem. And then here we have this one. Every time we take one out and then we in queue, take one out in queue until the one actually we take BO out, right, and in queue back again. If it is not so here this thing can be implemented. Say so first time I have a BO, so BO is no queue, so BO will return to the queue again. And this one David is a queue, so take out David. So what happened is like what happened is like first one I have BO, so that my BO go back to return to there. And the next one is David, so kill David. Next one Susan return. And the next one we have Jane, so Jane killed. Next one we have Ken return. And then next one we have Brad killed. So then we have the 3 left. It will be Bill, Susan, and Ken. And then this one actually Bill return. I'm sorry, this one actually Bill be killed. And then this one Susan return. And then this one Ken's kill. So the end we will end up with Susan. So that actually use that you can actually mimic that. 7 people, you will end up with Susan, right? 7 people, you will end up with that. That's the hot potato simulation. Is that okay?
Yeah.
So let's look at the program from this one. So it's actually using Q can solve this problem. That's what it tried to demo. So this one's unit 3. Let me pull up this directory. So here is a demo. Let me bring out another one. So I may go to example here. Okay, here is a potato. I'm sorry. So here we have the hot potato. So let's look at the hot potato. So hot potato, basically you have this, right? I need to copy the queue over here. I need a queue. So here let me see. The queue class. Let me actually find the queue. So let me this one is that there's a queue. Okay, let me bring up this one. Wait, it doesn't move. So here it should have a queue over here. Here it has a queue. So let me copy this queue portion over. And here, let me pass the queue over here. Okay. And right here, let me actually bypass this one. So what happened is that we have this hot potato problem, right? So every time we have a hot potato at least, and the number of the people we have 1, 2, 3, 4, 5, 6. Okay, this one actually 1, 2, 3, 4, 5, 6. We have 6 people, right? So actually 6 people, we will end up with 1, 2, 3, 4, 5, 6, 7, 6. And then we will try to actually, each time we, first we enqueue everybody into the queue. So we have the Bill, David, Susan, Jen, Ken, right? And every time we actually DQ one and then enqueue it. And then that actually, we keep doing that and then we actually DQ. So we use the number 7 each time we actually remove after 7 pass. After 7 pass, we remove one guy. Okay, so that's what it ended up to be. So that's the hot potato. So it actually, this one is a modified version because it actually every 7 pass of it we remove one. So basically starting from BO. So basically starting from BO. We start to count 1, 2, 3, 4, 5, 6, 7. Kill this one. 1, 2, 3, 4, 5, 6. No, 6, 7. Kill this one. 1, 2, 3, 4, 5, 6, 7. Kill this one. 1, 2, 3, 4, 5, 6, 7, kill this one, right? And then this one, 1, 2, 3, 4, 5, 6, 7, kill this one. So that had the Susan that. Is that okay?
Yeah.
So that's what this hot potato is. But this one actually is a general case for that just for us problem. Okay, more complicated, but it's actually to help you to simulate it. And in terms of theoretical result, I think this one is probably hot potato, probably even harder than the discussion we had for that just for this problem. So we don't go into that. That actually kill a lot of time, but the mathematical proof doesn't actually teach us much. Note that this example is a value of counting constant is greater than the number in the list. This is not a problem since the queue acts like a circle. So every time you DQ one and put into the queue, DQ one and put into the queue. That's the part you need to understand. So when you face a problem and you do simulation, you just need to know what should I use my data structure to mimic it. And then you actually allow the operation like this one, the hot potato. You know that every time you pass 7 people, so you just DQ, InQ, DQ, InQ, DQ, InQ, DQ, InQ, until that count up to 7. You reset the counter and kill one guy, take that guy out, and then start to do DQ, InQ, DQ, InQ, DQ, InQ, until the 7 reach, then you DQ another one, you know? So that's the way you do it. And the one actually for just for this problem is like, it's different. It's actually you have put the 41 people into a queue. Then I pass 1, kill 1, pass 1, kill 1, pass 1, kill 1, pass 1, kill 1. Same thing, you can pass 1, you can return it to the queue, in queue. So it's like DQ, in queue, right? Then DQ,
DQ in queue, DQ, DQ in queue, DQ, DQ in queue, you know, that kind of operation should be able to mimic the Josephus problem, okay? So the next one is application of queue. So application of queue, sometimes the printer simulation is usually for a big issue to use queue. So queue is not hard, but there's only one problem, is the latency problem. We don't want someone who try to print something, but because it's not prioritized, so or there's a guy who print like 300,000 pages, but other students, they may only have one page. So there's a latency problem we need to deal with for the printer task. We try to minimize the time for printing tasks. So 20 tasks per hour means that on the average, there will be one task per 180 seconds. So that can be calculated. So main simulation step, we create a queue called print queue. And then each task will be given a timestamp on its arrival. So when the task being assigned and put into the queue, we put in a timestamp. And then when you get out, we actually get another timestamp. Then we don't know how much time is spent. And at the end, we calculate on the average how much time the queue job stay in the queue. So for each second, current second, does a new print task get created? If so, add it into the queue with the current second. So whenever there's a task going to the queue, we put a timestamp on it. You know, so it's just like when you generate a hamburger, right? McDonald's trying to create a hamburger. So each hamburger like this, like 503, we put a hamburger there. 503, we put a hamburger there. 504, we put a hamburger there, right? And those hamburgers will be created all the way until there's one guy order, okay, take this one, take this one, take this one. But there is a requirement that, okay, all the hamburger generated by our hamburger cooker shouldn't be too fast. If it is too fast, there might be some hamburger past 3 minutes, nobody pick up. Those need to be dumped. You know, for McDonald's, something like that. But if you actually generate a hamburger too late, then we don't have enough. The whole queue may be empty. So people will be waiting for your hamburger. Is that okay? Same thing here for the printer job. We need to put a timestamp on there so we would know that, okay, when a print job being executed, how much time it takes. So if the printer is not busy, and if the task is waiting, remove the next task to the printer queue and assign it to the printer, and then subtract the timestamp from the current time, compute the wait time for that task, and then append the wait time for the task into a list for later processing. So each time a task put into a queue, get out to the queue, we know calculate how much time is spent. Based on the number of pages for the print task, figure out how much time required. And the printer now does the 1 second of printing if necessary. It also subtract 1 second from the time required for the task, okay, whatever. And then when the simulation complete, calculate the average time for a wait time to be generated for each print queue. Okay. So this is what in your data structure would be studying something like this to solve problem. But the fundamental data structure you use will be those kind of list, node, and also those kind of tree and graph. Okay. To design this simulation, we will create a class for 3 real-world objects: printer, task, and print queue. The printer class will need to track whether it has the current task or not. If it does, then it is busy. And the amount of time needed to can be computed on the number of pages in the task. The constructor will allow the page per minute setting to be initialized. Okay, whatever. So here we have a printer class. We have the page rate. So how many ppm, page per minute, that printer can serve. And then initially the task is none. Time remaining is none. Okay, when there's a tick, we increase the time. So the time remaining will drop. Okay, and if it is busy, if the current task is not none, we have someone using it, then it's not busy. The printer is not busy. Someone using it, then the printer is busy, and if not, it is not busy. And start next, you initiate new task. Okay, So there's a task class. The task class will represent a single printer task. When the task is created, a random number generator provides a length of 1 to 20 pages. So basically, it mimics a number of pages, okay? And the function is range 1 to 20, not including 21, okay? So each task will need to keep the timestamp to be used for computing the wait time. The timestamp represents the time the task was created and placed in the printer queue. The wait time method can then be used to retrieve the amount of time spent in the queue before printing begins. So here is the task class. You have the whenever there's a task, you create a timestamp for it, and then you generate the number of pages to be printed, and that number of pages printed will be used to calculate the wait time, the process time that you needed. Okay, then there's a main program. So now let's go to the program to simulate. So the end of the simulation should be like this. Okay, let's look at the program. So this one is called printer simulation. So in this printer simulation, basically you have a import random, and then you create a queue class, printer class, and then you have the task class and simulation. So this simulation is like you have the number of seconds to be simulated, and you have a page per minute, that's ppm, okay, to be set. So your laser printer, we create a printer of the page per minute, certain page per minute. So that ppm be passed by page per minute. So you will set up your printer will be processed in a certain processor rate. Okay. So basically, you create a queue, and that is actually empty in the beginning, and the wait time is empty because no one actually retired from the printer queue. And then you start to advance your current second, so from 0 to number of seconds. And if there's a new printer task, then we create a task of the current second, and then include the task to the printer queue. Okay, so there's a queue put into the printer task. And if the printer is not busy and the printer queue is not empty, then we dequeue from the printer jar and assign to the next task. And that next task will, based on its number of pages, to calculate the wait time for that task. Based on the wait time for that task, there's a wait time you calculate it, and then you put that wait time, total time into the your list, and at the end you actually sum up the total wait time list and divide it by the number of the process time, and then you calculate average number of the service, and then you will print out the average time served by the printer. Okay, so we can actually run it. Okay, so you will actually run for certain cycles, simulate for certain cycles, and it actually will end up with different number of tasks in the remaining in the queue. So if it is fast, you will consume the task, and then maybe something still in the queue. So basically, you only run this one, only run this for something, and you call simulation, and simulation call the next printer task. Okay, so that's for queue. This one is for queue. So that's chapter 3 for queue. Okay, so that's a queue simulation. Got this, and that actually is not a super hard problem for the queue. And we had the program right here and the simulation data right here. And discussion. Discussion queue maximum wait time latency is an issue. So we try to minimize the maximum latency in the queue. Okay, that's the design problem. And this type of simulation is called Monte Carlo simulation. Okay. Okay.
Mm-hmm.
Okay. Thank you now. Bye now.
Bye.